Assalamualaikum and hello everyone. Welcome to the video for 3.2 Nernst equation. In this video, we will learn to write the Nernst equation for a given galvanic cell and explain the factors that affect the cell potential. Okay, so on your notes, you'll be on page 8. So what is actually a Nernst equation? It is used to calculate the cell potential at non-standard condition, or we call the cell potential as Eᵒcell. Previously, we have learned how to calculate the Eᵒcell, which is E0 cathode minus E0 anode, or kakak tolak adik. Okay, for this equation, if you realize we have not here. Not means that the reaction is at standard condition. And what is actually a standard condition? That is actually when the concentration of electrolyte is 1 molar, pressure is 1 atm, then temperature must be 25 degrees Celsius. Okay, but not all the reaction will follow the standard condition. Maybe the concentration is not 1 molar. So how do we calculate the Eᵒcell? We can't use this formula. Okay, to calculate the cell potential, which is not at standard condition, we will use the Nernst equation. So the Nernst equation is Eᵒcell equal to Eᵒcell minus RT divided by NF ln Q. So R is actually a universal gas constant. T must be the temperature in Kelvin. N is the number of electrons transferred in redox reaction. Okay, remember when you write down the overall chemical equation, the number of electrons must be the same, right? So that is actually your N. The F is the charge of 1 mole of electron, which is equal to 96,500 coulomb. And Q must be your reaction quotient. But then what is your reaction quotient? Reaction quotient here is the concentration of product divided by concentration of reactant. Okay. So that is actually for the formula for the Nernst equation. Next, we will look for the factors that will affect the cell potential. Okay, so the factors that I'm going to discuss here, I'm going to talk about when the Eᵒcell higher. I want my standard cell potential to be a bigger value. So if I want my Eᵒcell to be higher, okay, what should I get? It's actually my Eᵒcell must be a bigger value, but my RT divided by NF ln Q must be a smaller value. Because why? When the value here is small, my Eᵒcell will be equal to my Eᵒcell. Okay. So for the factors, what we're going to look at is actually the Eᵒcell here, the temperature, as well as the Q. Okay, so for the first factor that we're going to look at is actually the concentration of reactant and product, which is actually about Q. So again, my Q here is from this term. So we want this term to be a small value. Okay, so how to get this one to be a small value? Is to increase the concentration of the reactant and decrease the concentration of product, which will increase the Eᵒcell value. Okay, so when the concentration of product is small and the concentration of reactant is high, here we will get a small value. So when we get a small value, when we substitute here, so this term we will get a small value as well. Okay, the second factor that we will look at is actually the temperature. Again, from this term, what we want to be a small value, so it means that the temperature must be a small value as well. So when this term is a small value, so this one will be a higher value, the Eᵒcell. Last but not least, we're going to look at the type of half cell, which is regarding our Eᵒcell itself. So here it mentioned that the half cell with more negative value, the Eᵒcell, as anode will increase Eᵒcell, and the half cell with more positive value as cathode will increase the Eᵒcell. Okay, so what does it mean? Okay, cathode is actually the value with a more positive value, while anode must be the one with more negative value. So for example, if this value is more positive and this one is the value will be more negative, so what we get is actually the Eᵒcell will get a higher value. So when the Eᵒcell will get a higher value, so subsequently, we will get the Eᵒcell to be a high value as well. Okay, so that is the general factor. Okay, here is actually maybe it's quite vague because I do not include the number as well. So that's why it's just a bit of explanation about the factors itself. Okay, next is actually we will write down the Eᵒcell equation. So how we write down the Eᵒcell equation? Okay, but then when we write down the Eᵒcell equation, we will not write down this one. Because actually, we will write down the Eᵒcell equation when the temperature and the R as well the Faraday is substituted. So we will get this one. Eᵒcell is equal to Eᵒcell minus 0.0592 divided by N log Q. Okay. What is N? N is the number of electrons involved in redox reaction. Q is actually the product of a reactant. Yeah, but for this one, we will consider the gas and aqueous. Okay, again for chapter 3 here, the phase is very important. Okay, from your question itself, usually it give you the E naught. From previous example, when you look at it, the equation does give you the phase. So that's why the phase is important. Okay, and then when gas is considered, it's actually because we want the pressure, while aqueous, we will consider the concentration. So when we write down the concentration, will be a square bracket. If gas, we just only going to write down P of the species. Okay, so without further ado, let's look for the examples here. But then example A and B is just a general equation. Okay, so first equation we have A plus B C plus TD. Okay, so the capital letter is all the species itself. And then the small letter is the stoichiometry. So for example, I'm going to take, for example, I have my N2 plus 3H2 is equal to 2 NH3. Okay, so NH3, H2, and N2 is my species. The number 3 here, the number 2 is what I call the stoichiometry lah. Okay, so this general equation, maknanya stoichiometry is the small letter. Yang big letter ni is the species. Okay. So how to write down the next equation? Okay, first I'm just going to write down yang Eᵒcell equal to Eᵒcell minus 0.0592 N log. Okay, here we know the log Q. But then when we write down the equation, we have to be specific. What is Q? Okay, remember here, for the phase, we will consider only gas and aqueous. So all of the species involved is aqueous. So how do we write it down? Okay, log product over reactant. Product is my C and D. So this is my species. So for the concentration, we have to write down the square bracket. So C to the power of C because of the stoichiometry, and D to the power of D. So this is my concentration of product divided by my reactant, which is concentration of A to the power of A, concentration of B to the power of B. So that is the general one. So if you are a bit confused, no worries. Later we will look at the example for the specific equation. Okay, so that is the equation A, example A. Okay, example E is the one with aqueous and gas. Okay, again, for Q, we will consider gas and aqueous. Okay, so first we have to write down all over again the Eᵒcell here. Log Q, okay, Q. So we have our aqueous. So aqueous here, the product over reactant, the product is C. And the C is our aqueous, so it must be the concentration. So we will write down the square bracket C to the power of C. Okay, and then here we have D, which is a gas. So how we will write it down? It will be a bracket, pressure, P stands for pressure, pressure of D to the power of D divided by, when we look here, we have species A and B. A is the gas. So again, pressure of A to the power of A. Okay, and then we have the B species, which is an aqueous, so we have to write down B to the power of B. Okay, so that is the general equation for A and B is the general one. Okay, but then C and the F here is actually a specific one. So let's do it together. For example, C. Okay, so here we have my equation. So again, Q. Remember that for Q, consider gas and aqueous only. So for this equation, when we look here, we do have solid. So is the solid considered? No. So we will just cancel out lah. Just going to cancel out this one. Okay, so what we have here is copper 2 plus and zinc 2 plus, which is an aqueous. But again, Q must be product over reactant. So product is zinc 2 plus. Okay, for concentration must be square bracket. Okay, here to the power of, here if we don't have any value, it's actually to the power, we have 1 kan. So, you don't have to include to the power of 1. It is understood, it is to the power of 1. Divide by my reactant, which is the Cu2 plus to the power of 1. Again, you don't have to write down the to the power of 1 here. Okay, so that is actually for C. Okay, again, consider gas and aqueous only. So if we have solid, we have liquid. Okay, so we have to we ignore that. We don't have to include it in Q. Okay, last one, I'm gonna look together. It's actually example E. Okay, we have our gas here. So how do we use it? Okay, remember log Q. Q is actually product over reactant. Okay, product is 2H plus and 2Cl minus, which is an aqueous. So aqueous, we must use the square bracket. So square bracket of H plus, but then here we have 2 in front, so we have to write down to power of 2. And then we have Cl minus again, we have 2 in the front, so we have to Cl minus to the power of 2, divide by the gas. Okay, so how do we write down for the gas itself? Here is H2 gas. So again, pressure of H2. Okay, you don't have to include the power of 1 because it is understood. And then Cl2, again, it is a gas, so pressure Cl2 gas. Okay, so that is actually how you write down the Nernst equation. Example D and F, I believe you could try yourself. Okay, so that's it for this video.